Okay, so thanks very much for giving me this opportunity again. So the goal of today is to start from where Callum left yesterday, namely was talking about the minimum model program for foliation rank 2. And today we're going to talk about minimum model program for foliation rank 1, especially on tree fruits. Okay, so the picture in many points of view is similar to what Callum was describing, but there are many subtle differences. So the goal of today somehow is to analyze some of these differences. So let me just start with the setup. As usual, work over the complex numbers, and X will be a normal projective variety. Of dimension n. Okay, so what is a rank 1 foliation? Well, clearly it's given by a subsheaf of the tangent sheaf of X of rank 1, which of course is saturated in the sense that quotient does not have torsion, and automatically satisfy the fact that it's closed under the brackets because it's rank 1. So in particular, we can think of it in the smooth locus of F. And X. This foliation is defined by a section of Tx. So what is a section of Tx? So we can think of it to be a non-zero vector field. Or in other words, we can think of it to be a derivation, something satisfies the Leibniz rule. So namely, and actually, in general, we will always assume that Kf, the canonical sheaf associated to F, is Q-Cartesian. So this implies that up to taking some cover, we can make it. We can consider foliation induced, and it will be Cartesian. I mean, the canonical sheaf will be Cartesian. And what is the advantage of doing that? The advantage is that, again, if Kf is Cartesian, then is defined by the foliation is defined by a derivation. So what is the advantage of doing that? One of the advantages is to study the singular locus of the foliation. So for instance, just as an example, but this will be crucial for us in what we're going to talk about, let's suppose that X is a smooth point of the variety, but such that X is contained, it's an isolated point of the singularity of F. So in other words, the underlying is smooth, it's a manifold, but we have a foliation where X is a singularity. It's just a point with a singularity. Okay, then in this case, it's easy to check that if M defines the ideal of X, then the derivation makes M invariant. So in other words, M is mapped inside M. Why? Because every function will be 0 at the point X once we calculate the derivative. And by the library, we can take powers of M, and it follows easily. It's just an easy calculation that for any power k of M, this is contained inside M. In other words, Mk is also invariant. So we can think of this derivative, this foliation at the point X, to be an endomorphism of this finite vector space. So this implies that we have an induced endomorphism from this quotient to itself. Again, this follows from the fact that the point X is invariant with respect to the. Okay, so why is it good? Well, because we can just, of course, these are finite dimension vector spaces over the complex numbers, so we can use basic linear algebra. So in particular, by using the Jordan decomposition, we can write delta, I mean, the part, we can compose delta k as the semi-simple part. I should be more precise and write k here, and the normal, and the nilpotent part of this endomorphism. So this is again for any k. So maybe I should write it. This is a semi-simple part, and this is the nilpotent part. So what is, I mean, clearly this is just linear algebra. We can do this for infinitely many of k, I mean, for all the value of k. So in particular, we can think of this decomposition to hold on the former neighborhood of the point x. So like Michael McLean said, from a formal point of view around the point, foliation rank 1 looks very much like linear algebra. I mean, it's a tool of linear algebra pretty much. So let's see why this way of writing is useful. Well, because thanks to a theorem by McQuillan and Panazzolo, we can characterize singularities of the foliation by using simple tool of linear algebra. Namely, for instance, just to give an example, f is log canonical at x, assuming that x is an isolated singularity. Then f is log canonical at x if and only if the semi-simple part is non-zero, where by this we mean the limit of all the semi-simple parts that we got by taking k equals to infinity. So I'm not sure if we define log canonical in the last 2 days, but somehow it's one of the singularities that play a role in the name of the program. It's a little bit weaker than canonical, but we'll see some of the other characterizations. So just to give an idea, we can find coordinates x1 and xn around x, and numbers lambda 1, lambda n, such that we can write delta s simply as the sum of the linear combination of these derivations. So somehow the linear part, the semi-simple part of the foliation is very simple to write down. As long as one of these ndi is non-zero, then our foliation is log canonical at the point x. So the idea is that, like in the case of foliation rank 2, we want to consider resolution singularities of these foliations. So what does it mean? So this story is similar to what Callum was talking about yesterday, but let's see some what the result is. And at the moment, the result is known to be true only in the case of threefolds, although it's a conjecture to be true in any dimension. So the theorem is due again by McQuillan and Panazzolo, and I think it's 2013. And it states that, let's suppose that F is a rank 1 foliation on a threefold X. Then we can find the sequence of weighted blow up. So I will not define what a weighted blow up is, but it's something very similar to simple blow up, and it's very much from toric geometry. So it can be easily described by using toric geometry locally around the point we are considering. So let me write the sequence as this. So in such a way that the induced foliation of on xn will have canonical singularity. So there is a difference in the case of foliation rank 1 respect what happens in foliation of rank 2. Namely, although we improve the singularities of the foliation, we could create new singularities on the underlying variety. So what does it mean? It means that even if we start from X smooth variety, we could have that, because of these weighted blow-ups, Xn becomes singular. But fortunately, the singularities of Xn are well understood. So let me just say that as a remark, note that Xn has always quotient singularities. And we can even be, and thanks to the theorem of McQuillan and Panazzo, we can even be more precise. Namely, either F is terminal, sorry, Fxn is terminal, or Fxn is canonical, but Xn has Z2 quotient singularities. And actually, what they do is to describe very carefully what happens in this case, namely how the foliation look like. So in some sense, it's a very satisfactory result. And actually, they show with an example that we cannot hope for a better result. Namely, if we want to improve the singularities of the foliation, we might need to create singularities of the underlying varieties. So since I'm going to use this later, I'm just going to call these singularities as admissible singularities. We could just call it canonical, but just to make sure that we are in this setup, I'll just call it admissible. And we can, I mean, if you want to run MMP, we can start from here somehow. We'll see that this is a good set of singularities from MMP point of view. Okay, just to see more example of results in foliation rank 1 by a theorem of Bogomolov and McQuillan, which we will use later, although I was stating a slightly different version. We know that if X is smooth and F is terminal, terminal is the singularity that appear in my first talk when I talk about classical MMP. So it's the mildest, among the singularities that appear in the MMP, this is the mildest set of singularities. So in this case, F actually happens to be smooth. So in other words, it's if you know that the underlying variety is smooth, then being terminal, being smooth is exactly the same. So what plays a role here are canonical singularities. And in the same paper, Bogomolov-McQuillan proved that both the bend and break and the cone theorem hold. Actually, here in both of these results, I'm not assuming that the dimension of n is 3. So here we are assuming that n is any number which is greater or equal to 2, I suppose. The interesting case is from 3 upwards. So in this generality, for foliation rank 1, maybe I should write it rank 1 foliations, the bend and break and the cone theorem hold. So we talk about this few times, both in the classical MMP and then in the case of foliations. The result is exactly the same. But let me mention a few words about the bend and break, because it has, I mean, it comes from an even stronger result. It's even a nicer result. Namely, the theorem is this. Assume that we have, let's suppose that X is a smooth variety for simplicity. Again, no assumption on the singularity. And let's suppose that F is any foliation. In this case, this is the only result where I'm not assuming the foliation to be of rank 1. And let's suppose that C is a curve such that the foliation is defined by subshift. So the shift that defines the foliation is ample on the curve C. It's an ample vector bundle. So this means that if we take the projectivization of this vector bundle, then the tautological line bundle is ample. Okay, under this assumption, then for any point of the curve, sufficiently general, the result is, I'm taking a small subset of the result, but let me just state in this form. The leaf of the foliation is algebraic. and is rationally connected. So in other words, the picture looks like this. We have our curve C, and for the gel pointer X, not only we can find rational curves, we can actually find a leaf, which is algebraic, which contain lots of rational curves. Namely, for any 2 points of this leaf, there will be a rational curve joining these 2 points. So in particular, if the rank of F is equal to 1, then to say that EF of C is ample is exactly the same as saying that AF times C is negative. And so somehow, at least in the smooth case, this reproduces the bend break. The bend break is a bit stronger, but this weak form, like we saw on Tuesday, holds. Okay, so now we go back to the main model program. These are, as usual, the main tools like we saw in the last few days. These are the main tools of the main model program. And so now we want to see how to use these tools to produce a mirror model. So in this direction, there is a theorem by Michael which solves this problem in full generality. Namely, it shows that if F is a foliation on a normal variety X, on X with quotient singularity, and F is canonical or even low canonical, then what it shows is that we can find a minor model. Namely, we can find there exists a rational contraction such that the induced foliation of on Y, sorry, I should have said F is canonical and the canonical device of F is effective. Otherwise, there is no hope to find a minor model. So this means that, I think it was explained before, but this means that perturbation of KF is big. So such that the induced foliation on Y has NF canonical divisor. So in some sense, this is very satisfactory. We can always find a minor model for any foliation. I forgot to say them. Of course, we're assuming that of rank 1. Sorry. And we're not assuming anything on the dimension of X. Then the way that Michael proves this result is by basically gives a very detailed analysis of what happens in the Balassian geometry of foliation. So somehow he studies singularities very carefully in order to produce what happens at each step. But it's not quite an MMP. So the result that I would like to talk about, which is a result with Guillaume, is that if we work in dimension 3, I will explain why we are interested in this kind of result. So if F is a foliation of rank 1, with admissible singularities, so remember this means, oh sorry, and I forgot to say, on a threefold X. So by the theorem of Macquillan and Panazzolo, we can always assume that our foliation, after taking blow-ups, we can always assume our foliation has admissible singularity. So this is not some kind of restriction. So in this case, we can run MMP in order to get a mirror model problem. So such that, again, we assume that the canonical divisor is effective. Then there exists a sequence of steps of the MMP such that, so flips of divisorial contraction, such that the induced foliation is minimal. So in other words, Kf for xn is an F. Okay, why are we interested in this? Well, first of all, we would like to understand more carefully what happened, well, how to produce the mirror models. So in other words, we can really show that the mirror model program is obtained by, exactly like in the classical mirror model program, by running standard operation like flips and divisorial contraction. And also probably the main reason why we're interested in these results is because somehow the proof follows the same ideas, at least from some point of view, of the proof in the case of rank 2. So it's some kind of hope, there's some kind of hope that such a proof can be generalized in any dimension and for any rank, because you use similar methods as what Callum talked about yesterday. So let me say somehow what are the main tools that we use in order to prove such a result. So first of all, let me start from what I mentioned already before. So this is a proposition. Let's suppose that from x to x prime is a step of MMP for a foliation F. Then what we show is that if F on X has unmissable singularities, then also X prime, then also the foliation F prime, which is induced on X prime, has unmissable singularity. So in other words, we don't leave this category. We continue to work on this category. So it's a good set of singularity to work with. And again, it's not, since we can always assume that after taking blow-ups that foliation has unmissable singularity, so it's, from variational point of view, it's the right, it seems to be the right context to work with. Okay, so let's see. How to proceed now? The idea is that we want to use the cone theorem to produce a curve and then contract it in such a way that we proceed with the mirror model program. So let me give an idea of the proof. I'm going to idea of the main proof of main theorem. In other words, existence of a mirror model program. So by the cone theorem, we can assume that, of course, Kf is not an F. Otherwise, there is nothing to do. And by the cone theorem, we know that there exists a curve which is extremal with respect of the cone of curves and which is negative with respect of Kf. So there exists R, which is an extreme array. So it's spanned by a curve C. So it's a extreme array of the cone of curves on X, which is Kf negative. So in other words, Kf times C is negative. Let me use the bar because I will use similar notations what I used in the previous lecture. Okay, so now the idea is that we want to look at the locus of this ray and we want to contract it. So since I'm assuming that Kf is set effective, we know that the locus of R, this is also a fact like mentioned by Callum yesterday, the locus of R, which is the set, the union of all the curves C, which are contained in the array R, this is a Zariski closed set. And we know by the fact that Kf is not set effective, so this has already been mentioned, BTPP, implies that it cannot be, the locus of R is not the whole X. So since I'm assuming that X is a threefold, there are two possibilities. Either it's a curve, well, it's not X. So either it's a curve or it's a surface. So I'm going to consider this case here, which is the most interesting case. It's the case we mentioned, we talked about in the previous lecture, is the case of the flipping contraction. So the first thing that we do, and this is exactly like in the case of rank 2 foliations, it's possible to show, this follows from Artin's theorem, that we can contract, so assume it's a curve. So what is possible to show is that there exists a Banach contraction from X to Z. So such that the exceptional locus of psi is equal to the locus of R. But unfortunately, we cannot quite say that Z is algebraic at this point. I mean, not an algebraic variety. What it is at the moment, since we are using Artin's theorem, and Z is an algebraic space. But this does not, I mean, a posteriori does not create any problem for us. And we'll show that a posteriori will be algebraic. Okay, so let me draw a picture exactly like in the case of the classic MMP. So this is X, we have our curve C bar, which is contracted to a point. So this is outside. So what we want to do is we want to flip this curve. We want to find, we know that Z is too singular to work with, so we want to replace X by some other variety here, which it's also mapped into Z, and which emits a curve on which is positive, Kf is positive. And the idea is very similar to what Callum was talking about in his previous lecture. Namely, we want to find some divisors on such a way that the C bar becomes negative with respect of Kx plus delta. So the idea, very vaguely, is that we want to find delta such that Kx plus delta is negative with respect of C bar. If we can do that, and sorry, I should say, and X delta is log canonical. I mean, the singularity of X delta are under control. They belong to the set of singularities that are miscible for the minimum of the program, of the classical minimum of the program for threefolds. So one step that we copy exactly as in the case of rank 2, the one that we did before, is the fact that we are free to work on a formal neighborhood of the curve C bar. This takes some work, but this work was explained by Callum yesterday. So, as in the case of rank 2, we can, it's enough to construct such a device of delta on a formal neighborhood of delta, or on a formal neighborhood of C bar. Okay, so how do we do that? Well, actually, it turns out that this is more difficult than the case of, at least for us, it took us more time than in the case of rank 2 foliations. Let me explain some of the ideas that we use. So first of all, it's possible to show, this is due to Michael actually, that there exists exactly one point on which, there exists exactly one point on C bar, X on C bar, on which F is not terminal. I mean, assuming that this is the picture is the flipping contraction, then it's possible to show that the only interesting case is when C bar is actually P1, and there's only one point on which F is not terminal. So we want to construct delta in such a way that it contains the curve C. So as a first approximation, we can do it in such a way that this exists in a neighborhood of X. And this is fairly easy. It's possible to study by using, let me say a few words about that. By using the picture we saw at the very beginning today, it's possible to show that there are some invariant divisors which play the candidate for delta. So how to do that? Well, as we mentioned, X is a singular point. So around X, we can write the foliation. There's a bit of work to do because it's not true that it's Gornstein in general. So we might have to take covers, but this is not the most technical problem. So I will skip some, I will cheat a little bit. Assuming that it's Gornstein at the point X, we can write delta S plus delta M. Well, delta S was very clearly described by linear algebra by choosing a neighborhood, I mean, some coordinates on the neighborhood of X. And so for a suitable choice of this coordinate, then we have that some of these hypersurfaces will be invariant. And it will play, I mean, will be one of the components of delta. What is the problem? Again, the problem is the fact that we can only do this game locally around the point of the single locus of F along C bar. Of course, in the smooth points, it's easy to show that this is doable. The problem is that how do we glue them together? So, and this is what took us some time. So let me explain some of the tools that we use to solve such an issue. So what is easier? I mean, let me pretend for a moment that we can move the foliation from X to Z. So let me go back to the picture we had before. Just now we had the foliation defined on X, which was giving a foliation on Z in such a way that the curve is mapped to a point. So maybe instead of creating these hypersurfaces on X, we can do it on Z in such a way that our invariant surface contains the, so let me call Fz the foliation on Z, which is well defined, and Z the image of, the little z will be the image of the exceptional locus, so the image of C bar. So the idea is that we would like to find something like this green surface, an invariant surface which contains the singular point. What is the problem? The problem is that, as we mentioned in the first lecture, Z is too singular. And so let me write, but KFZ is not Q-Cartier. So this method does not work because it doesn't matter how many covers I take, we will never be able to write KFZ as defined by a derivation like we did a few minutes ago. So we have to do something slightly different. And what we do is this, instead of descending, so what we tried to do just now was to try to design the foliation F and work on the new, with the new foliation. But instead of that, what we can do is find some kind of perturbation of our F in such a way that this is possible. So I will skip the proof, but one of the steps, so ingredient, proof, we can show that there exists a surface D on X with mild singularities, so surface divisor, such that F plus delta plus D is Q-Cartier. This is easy. But what is important is that, and there exists an M, positive integer, such that M of Kf plus D is equivalent to 0 in a neighborhood of C. So you see, F is negative on C bar. So, and C bar is just P1. So along C bar, it's very easy to obtain such equality, right? Because Kf times C bar is actually -1. So we just need to find a surface which meets the curve in one point. The problem is that it's not enough to show it to be true on the curve C. We want to show it in a neighborhood of C bar. And so this requires a bit of work. But what is the advantage of doing this? The advantage of doing this is that now this pair descends to Z. So we can think of this to be a foliation with a singularity along D, so dimension 1 singularities. So if you force the foliation to have a divisor which is a singular locus for the foliation, then it's possible to descend it to Z. So there exists, if dz is the strict transform of D, or just the image, sorry, then what we have is that this is Q Cartier on that. And we can work with this foliation. It has singularities which are of convention 1, but it behaves very much like classical foliation rank 1. So what is the advantage? Well, again, there is another ingredient, so this is ingredient 1. Another ingredient of the proof is that by, I just sketch it briefly, by embedding Z in a smooth project, in a smooth variety around the point small z, which is the locus where the curve C bar maps to, it's possible to show that it behaves almost like a smooth foliation. So, of course, I'm hiding a lot of technical details, but by doing this trick, we can show that there exists invariant divisor for this foliation containing the point Z. Okay, and what is the advantage of doing this? Again, I'm cheating quite a bit because you see the pre-image of SI will not be Cartier, but they will contain Cartier divisor. It's possible to show that they contain Cartier divisor. So let me just write that this induce I induce some divisor S bar I, which is on X, sorry, which are F invariant. And somehow we can define delta to be the sum of this SI. Actually, 2 will be enough. 2 of them will be enough. And you see, for free, I mean, well, I didn't explain exactly, sorry, explain exactly how to obtain this S bar I, but by doing this, it's easy to show that the curve contained in delta and not in the support of delta. Not only that, it's possible to show that Kf plus delta, Kx plus delta is negative with respect of the curve. Now, what is the last step? We would like to say, okay, this implies that the flip exists, at least in a formal neighborhood of C bar, the flip exists. What is the thing we need to be careful of? Well, the thing that we need to be careful of is that we need to show that the pair X delta has bounded singularity somehow. The singularities of this pair are not too bad, because otherwise we cannot run the classic MMP. So let me just say it's low-canonical. And again, I'm hiding quite a lot of details, and I'm cheating quite a bit. But I would like to show an example, just to conclude, and just to show how to compute the singularity of X delta. This is similar to what Callum was talking about yesterday, but slightly more complicated because although we're going to use a junction does not, I mean, in general, it's not true that if you, so let me write it as a remark. It's not true that if S1 and Sn are F invariant, even if you assume that F is very nice, then in general, it's not true that the pair Xi is not low-canonical. It's very easy to produce example. Why? Because there are too many invariant surfaces, so you can just throw them inside, and at some point it will surely not be low-canonical anymore. So this is different from rank 2 foliation or 3-fold. So we need to be a little bit more careful about what kind of statement we can prove. And actually, what turns out to be true is that although written like this is not true, but in the right setup, we can show that there are at least over points, over close points, we cannot, there exists no divisor which has log discrepancy less than 0. This is a technical word, but what it means is that if it's not low-canonical, it would be not log canonical along a curve. So let me give an idea of the proof of this. So let's suppose that, so what we're going to show is that, so let's consider, this is true for close point. So let me consider a very special case. Let me suppose that, there exists a local resolution such that the exceptional locus for the pair x delta, such that the exceptional locus of mu, it's a unique divisor E, irreducible divisor. And mu of E is mapped to a point. There are not many possibilities. Since we are working on a threefold, either mu of E is mapped to a curve or is mapped to a point. Since we want to show that things are okay at least for points, then we can assume that E is mapped to a point. So let me draw again a picture. So we have, this is x bar, this is our original variety. So, and then we have some hypersurfaces which contain the curve C bar. And we know that one divisor, it's all we need in order to resolve singularities. And this E will be mapped to to the green point here. Okay, how can we proceed in this case? We would like to show that at least with respect to this configuration, the pair x delta is log canonical. So let's see the calculation. So first of all, it follows from the theorem that we saw Okomola and McQuillan, or at least similar tools, that this morphism is crepant with respect to foliation, which means that if f bar is the foliation induced on x bar, then kf bar is nothing but the pullback of kf. This follows also from the fact that the point that we are blowing up is invariant. Okay, and what else can we write? Well, let's write, let's just consider the case without, let me just prove that x is nice at the point. So let me consider what happened when I take the formula for the discrepancy in the case of x. So let me just write this formula here. So in this case, what I want to show is that A is not negative. So in other words, the goal is to show that A is greater or equal than 0. I'm not writing divisors SI. I could write a divisor SI and I get very similar calculation. I just want to show what kind of methods apply here, and what exactly we do. So first of all, we can use adjunction both for f bar and for the pair x bar E. So what does it mean? Well, first of all, let me start with the easiest one for the x bar E. Since everything is log smooth, what we have is that if we restrict this pair to E, what we get is just KE. Now, since I'm assuming that E is mapped to a point, mu star of kx restricted to E is equal to 0. So all we get is A times E restricted to E. And we know that since E is mapped to a point, minus E restricted to E is ample. So far I used adjunction for E, the pair x bar E. Now I want to do the same for KF. And on one side, I get 0. Why? Because I'm using this formula here. I'm using the fact that KF bar is equal to mu star KF. So since again, I'm assuming that the foliation maps to a point, the divisor maps to a point, we get 0. On the other side, similar to what Callum was talking about yesterday, what we get is adjunction for foliation, which is just given by a foliation G induced on E plus delta, where delta is some effective divisor on E. Sorry, there are too many delta. theta. Okay, so let me assume for simplicity that theta is non-zero. If not, this proof is not very different. So this implies in particular that kg is equal to minus theta, which means that kg cannot be self-effective. So this implies that E is uniruled with respect to the foliation. I mean, G is uniruled. Okay, and this implies in particular that E is covered by curves. Sigma, such that K times sigma is negative. Okay, but remember, we need to use the fact, we are going to use the fact that minus E restricted to E is ample. And so we know that minus E restricted to E times sigma must be positive. And we also know that this, up to this value A, these two divisors are the same. K is exactly equal to A E restricted to E. So by using these two facts, it follows, I mean, it's just arithmetic. If I didn't do a mistake, this implies immediately that A is bigger than 0, which implies that basically the log discrepancy is positive. So in other words, in this particular case, we got what we want. In the case theta is not equal to 0, then what we do is we use the classification of foliation with trivial canonical device on a surface. And we use some, and this is due to McQuillan, we use some analysis, but again, the idea is very similar. We want to compute the value of A by looking at what happens on curves covering E. And again, I've been hiding lots of details. For instance, I didn't consider device OSI, but modulo some technical details, this is exactly what is going on to prove what we want. Okay, I'm going to stop here. Thanks very much.